What are boundary conditions in CFD software simulations? Imagine you're trying to predict how water flows through a pipe or how air moves around a car. To do this accurately, you need to tell the computer how the fluid behaves at the edges of your simulation area. That's where boundary conditions come in. They are instructions that specify how the fluid interacts with the limits of the space you're studying. In computational fluid dynamics software, boundary conditions are essential because they set the rules for how variables like velocity, pressure, temperature, and turbulence behave at the edges of the simulation. Without them, the software wouldn't know what to do at the borders, and the results could be off or unstable. Think of it like setting the rules for a game. If you don't, the game can't be played properly. There are different types of boundary conditions used depending on the situation. For example, at the inlet, you might specify how fast the fluid is entering and in what direction. This could be a fixed velocity or a set flow rate. For example, if you're simulating air flowing into a duct, you might set the inlet velocity to 50 meters per second. This helps the software understand how the fluid starts its journey. At the outlet, you usually specify the pressure or let the software calculate how fast the fluid leaves based on the pressure. This prevents artificial effects like waves bouncing back into the domain, which can distort the results. For instance, setting the outlet pressure to atmospheric pressure allows the flow to exit naturally. Walls or surfaces within the simulation also need boundary conditions. The most common is the no-slip condition, which assumes the fluid right at the wall is not moving relative to it. This models real-world viscous effects, like how water sticks to the sides of a pipe. Sometimes, you might assume the wall is slippery, allowing the fluid to slide along without friction, or set a specific temperature for the wall if heat transfer is involved. Sometimes, the geometry or flow pattern is symmetrical or repeats itself. In these cases, symmetry or periodic boundary conditions are used. Symmetry boundaries assume no flow across the boundary, simplifying the calculations. Periodic boundaries connect opposite sides of the domain, making the simulation smaller and faster. In terms of math, boundary conditions are classified into three main types. Dirichlet conditions fix the value of a variable at the boundary, like setting the velocity to 5 meters per second. Newman conditions specify the gradient or how fast the variable changes normal to the boundary, such as zero velocity gradient. Robin conditions combine both fixed values and gradients. When setting up a CFD simulation, engineers need to carefully choose these boundary conditions to match the real-world scenario. For example, in designing a cooling system for an engine, you might set the inlet temperature and flow rate, specify the heat transfer at the walls, and define how the coolant exits. Incorrect boundary conditions can cause the solver to produce results that don't match reality or even fail to run. Most CFD software packages ask for boundary conditions for all the key solution variables. Some programs even help by suggesting appropriate conditions based on the problem. This makes sure the simulation stays stable and gives meaningful results. In real-world applications, boundary conditions help engineers understand how fluids behave in systems like ventilation, engine cooling, or aerodynamic testing. Knowing how to set them correctly is a vital skill in mechanical engineering CFD analysis. It ensures that the simulations you run are accurate and useful for making design decisions.